thank you all for coming to not the last session, but almost the last session. I brought Timbits, but slightly more people than I expected showed up, which is lovely, but hopefully you don't all want Timbits. But if you do after the talk, they're right there. Cool. So this is Scaling with Apache Spark, or a lesson in unintended consequences. I'm going to probably focus more on the unintended consequences because I think that's more fun. When things work, it gets kind of boring. To be fair, it's not like I've had a lot of experiences where everything's worked in my career, so maybe it is actually quite exciting. Let me know if you are. So I also do want to shout out, there is a content warning. This is not suitable for viewers who believe marketing material from vendors. This may occasionally say things like about how software doesn't actually work. And if you want to be happy and believe that Spark is perfect, this is probably not the talk for you. We're going to perhaps shatter some of those illusions. So I'm Holden. My preferred pronouns are she or her. It's tattooed on my wrist in case you forget. Despite that, people still forget, but that's fine. I'm a software engineer at IBM's Spark Technology Center in San Francisco. I really like it. They pay me to work on open source software. It's pretty exciting. If you're looking to work on open source software and willing to relocate to San Francisco, then come talk to me afterwards. I am an Apache Spark committer, which is really exciting for me and probably not very exciting for any of you. But if you have changes you want to make to PySpark, or you want to start contributing to PySpark, this is not that talk, but please come talk to me afterwards. And I'm always trying to get more people from outside of UC Berkeley contributing to the project, so that we have, if perhaps not a diversity of people, maybe a diversity of at least schools. I'll take what I can get. I'm a co-author of a few Spark books. I think High Performance Spark is definitely the best Spark book out there. I get much higher royalties on it than any other Spark book that's been published. It might not be very good for learning Spark, but it buys me almost a quarter of a cup of coffee in San Francisco. So that's exciting. If you want to follow me on Twitter, it's just my name, SlideShare. I didn't pick that username despite everywhere else, but whatever. Consistency is overrated. And yeah, so just outside of work, or perhaps in addition to work, I'm trans, I'm queer, I'm Canadian, which I know that one. And I consider myself a part of the leather community. Actually, so the Canadian one is I'm here on a work visa that y'all are considering changing, which is just a wonderful time to be in America. And I know we've heard this before, but please have, support your coworkers. I like to think that when all of us work together, we can make the same shitty software faster, and I get to go home and see my partner, and that's really exciting. So we should all work together. We shouldn't fight with people on the internet, and we can be nice people to each other. And you can remember we come from different backgrounds, right? Also, I remember the first time I met someone like me in software. I was really excited and happy. And so yeah. Whatever. The other person who's presenting with me today, her name is Boo. She has presented before the Texas State Legislature. They did not listen to her. She's lovely. She has a lot of experience barking at computers to make them go faster. And what else? Oh yeah, she got a Twitter account on this trip after I realized I've just been slacking on that. So please follow Boo on Twitter. She tweets about happier topics than I do. Right. Oh, my employer. Yes. I work for IBM. We have this lobby with a lot of green in it. Green is the color of a passing Travis build. So if you're thinking about buying software from IBM, think of this green lobby. I'm sure it only cost us a few $1 million, and it definitely says quality software. Yeah, my boss told me I have to put this slide in every one of my talks, but he did not say what I have to say about this slide. The fact that I've been doing this for 6 months means he does not listen to these, but that's fine. So yeah, I work with a bunch of other people in San Francisco. I'm co-located with a bunch of designers. In case you haven't figured it out yet, none of them look at my slides. This is not their fault. This is all on me. They're lovely people. They work on open source design, which is hard. And so it's great. If you consider buying things from IBM, maybe you work at a bank, please keep doing that. I like getting paid. So yeah, cool. Yeah, so what are we going to talk about? I'm going to talk about some of my assumptions about who you all are. You've been laughing at my really bad jokes, though, so that's just, oh, thank you so much. It's really sad when I'm just doing this stand-up / computer science routine and no one's laughing. We're going to talk about sort of the core abstractions behind Spark. We're going to talk about why Spark ended up being the way it is. And I think really that's the more interesting part. And incidentally, along the way, you might learn about how to use Spark more efficiently, but hopefully we'll learn about how to design things better. So you don't repeat the same mistakes we did, or if you do, you know what you're doing. Not that we didn't. Yeah, certainly not. So you're nice people. If you mind pictures of cats, this is not the talk for you. There are other talks by people who do not like cats as much as I do, although thankfully cats do seem to be very popular at Strangeloop. Probably no one's playing Pokemon Go anymore, which just breaks my heart, but it's all right. And yeah, so actually, how many people here actually use Apache Spark? Oh, crap. Okay, how many people do not use Spark? I think I see some of the same hands, and I am very confused. But that is all right. Okay, hopefully this will be good for both of you. For those of you that don't use Spark, it's a general purpose distributed system. Specifically, though, it's focused on the kinds of problems that we solve with data parallelism. It has a really nice API. If you think functional programming is good, and you probably do if you're here. It even has a Python API, which is useful. I work on the Python API a lot. It's an Apache project with all of the good and bad that entails. This is being recorded, so we won't go into either of those things. It's faster than Hadoop MapReduce, and I just want to say I love Hadoop MapReduce for setting the bar down here. I mean, like, it's great. Like, Hadoop MapReduce definitely gave us the ability to solve problems we couldn't before, but performance-wise, it left a lot of opportunities for Spark to improve on and other systems, and so it's very good. Normally, people come to Spark when their problems get too big for a single machine, or they've decided they want to find a new job, and so they're going to start using Spark so they can call themselves a data scientist. It has sort of two core abstractions, and we'll talk about why they're both terrible. So when I say distributed system, what I actually mean is there's 100 gnomes. They live inside of this thing. It's called AWS, or sorry, IBM Cloud. And when things go wrong, you can blame the gnomes. Unfortunately, sometimes Spark is responsible for coordinating what all these different gnomes have to do, and sometimes Spark really just decides it doesn't like one of the gnomes, so it gives that gnome all of the work. And then things take a predictable turn when that gnome decides to go out for drinks instead of writing software. And so yeah, okay, cool. Right, so why do people come to Spark? Ooh, oh, the cat pictures are so big. Yeah. A lot of people come to Spark because they are running a MapReduce job. It's taking 16 hours, and they're like, I can probably learn Spark in 16 hours. And you can. I have written MapReduce jobs that took longer to run than it did for me to learn Spark. Not all MapReduce jobs. The other one is, you know, my data no longer fits in Excel. And those people, thank you for buying support contracts. You probably could have used pandas, but more realistically, like the other way that we come to it is, I have a local problem, it's gotten too big to solve with the techniques that I'm used to. Oh crap, I have to use distributed systems. Yeah. So Paco does a much better version of the history because he actually knows all of these people and saw many of them, including taking them out for drinks when they were told their projects were canceled before they started working on the things that were Spark. But it came out of UC Berkeley's AMP lab, which is really awesome. It got rebooted into something called the RISE lab. I don't know, they change their name every few years, I guess, in case the papers aren't good enough to just keep that ball rolling. But the papers have been really good, and they still keep changing the name, so I don't understand their motivation. It's really similar to a lot of these other systems. If you're familiar with any of them, this will give you some context. If you're not, don't worry, no stress. So the sort of terms that I'm going to use really frequently are RDD, which is Spark's like generic distributed collection. It's called a resilient distributed data set. The resilient part is important because in distributed systems, failure is a first-class citizen. It's really, well, I shouldn't say it's really easy. It's comparatively easy to make a distributed system where we don't care about failure, but it turns out that IBM Cloud, while we don't have failures, some of the other vendors have hardware that fails. More realistically, like once you start running on 100 machines, your probability of failure starts approaching 1 over the course of any reasonable length of time. So you have to be able to recover from failures. Spark also has this thing called DataFrames, which often gets Python people excited. I don't see a lot of people excited. So either you've already gone down the disillusionment of figuring out that Spark DataFrames aren't DataFrames, or you're not Python users. It's fine, either way. But it's essentially just like a distributed data frame, which really doesn't have any of the operations you'd expect on a data frame. So all of the concepts you want, just with none of the useful things. And then datasets are data frames with types. Everyone loves types, or at least some people love types. The Spark developers are Scala developers, so they love types. And so data frames, we took types out, and then we went, wait, that was a bad idea. And datasets are data frames with types thrown back in. Cool. This is the really fancy diagram, which definitely convinces you. I don't have designers. But so it's important to know that Spark is a collection of things. It's got this sort of core execution engine, but we also have this fancy machine learning library, very good for VC funding. We have this streaming library, used to be pretty good for VC funding, now only sort of so-so. The language APIs are good for when we actually want people to use our software in addition to raising money. Now and again, so usage numbers though, very important, monthly actives. So Python and R are definitely in there. We have a collection of graph tools that don't work, and we have this other machine learning library that we just like to pretend doesn't exist. And community packages is the polite way of saying everyone who isn't us. Right, okay, so let's talk about one of Spark's core design principles, and that is laziness. Now, you're probably familiar with laziness, like it seems like a lot of people here have been exposed to Haskell, but Spark's laziness is a little different. It's more, so I like to use the teenager approach. You ask the teenager to take out the trash, you ask the teenager to take out the trash, you actually finally go and check, and then the teenager takes out the trash, right? And so Spark does this. You ask it to compute a bunch of data, and then you say, well, okay, on top of that, I want you to compute this other data, and some other data, and then that's fine. Spark's just like, yeah, I got that. And only once we finally ask Spark to like save the results out, Spark will be like, oh yeah, so about that, your input file just didn't exist, so I didn't do any of that. But so now, normally when you think of laziness, or at least normally when I think of laziness, I think of systems which are terrible to debug. And that's Spark. But on top of it, we use this laziness. We do smart things with it. So it's not just terrible things to debug. We're able to use some cool things about it. We got this really fancy graph. Ooh. Okay, no one's impressed. But like, you can see this graph of the different things that we've done in Spark, and we can see that there's these different stage boundaries. And so in Spark, a stage boundary is introduced where we have to like shuffle our data. So when the data can't be computed locally on a single node anymore for each partition, and maybe we have to like combine data by key, we'd end up putting in a stage boundary. But you can see that a whole bunch of things able to get sort of collapsed into a single stage. And if you are coming from a MapReduce background, you're probably used to spending a lot of time thinking about how to combine everything into a single map task, or trying to sort of reduce the number of passes you're doing over your data. And in Spark, though, the nice thing is I can write sort of more functional style programming without having to spend a lot of time manually combining my different map tasks and sort of trying to shove them together. Because the optimizer, when we finally force it to do the work, goes in and goes, oh, well, I can stick these 3 things together. And this thing from over here, yeah, come on, you can be friends. And then, it gets a little awkward if they use too much heap space, but otherwise, everyone gets along. And then on DataFrames, we have something very similar, except you can't actually understand what it says. So you can have a similar graph that shows you the execution. Once again, Spark is combining a bunch of things for you. It just, instead of saying useful things, says whole stage code gen, which means I put a bunch of stuff here. Good luck. So I am going to have everyone's favorite word count example. As a licensed big data instructor, you're not allowed to give a presentation without word count. It's why it's in every single one of these. But so this can illustrate Spark's really basic laziness. So the first line loads in some data, then we go ahead, we tokenize it with spaces. Because I'm in North America, I can pretend that's a reasonable tokenizer. And then I go ahead and I compute the word and the number 1 pair, very exciting. And then I go ahead and I tell Spark how to combine these results. So I say for everything with the same key, please combine it together. And then finally, OK, yeah, I should probably save this output. And so this is the action which actually forces Spark to do the work. Until this point, Spark has done nothing. Our input file called src may not exist. It might actually, we might not even be on an HDFS cluster. Spark wouldn't notice. All of these things could fail and be terribly wrong, and we would only find out here. But the important part is, right, this map task and the previous flat map task can get combined together into a single stage, right? So if I was working in a system where this was going to be done like a map and then do another map, I would actually want to explicitly have to combine these bits together myself. But Spark can do this for me for free, so I don't have to think as hard. Now, this isn't so exciting when I've chained 3 operations together, but when you start to get those really complex graphs, like on the previous slide, the automatic chaining is a lot nicer. So there's some total downsides to this, though, right? The pipelining part, really awesome. I got that for free. The complete lack of debuggability is really frustrating for a lot of people. Essentially, the fact that when I call this, I can get an error about my input file not existing is really something that takes getting used to, is a polite approach to it. It also doesn't help that Spark's stack traces are frequently around 400 lines long. So even once you do get the stack trace, figuring out what actually went wrong is a little painful. The other really cool thing is Spark uses this laziness to construct those graphs I was showing you, and those graphs are actually used to handle Spark's resiliency. And this is a very different approach than the MapReduce model. The MapReduce model says, I might lose some computers, but it's OK. I'm just going to write it out. I'm going to write my work out on persistent storage to a bunch of different machines. So if something goes wrong, I can go back and find it, right? I'm not going to lose all of my HDFS nodes, right? If I do, something really terribly wrong has happened, and we probably weren't going to be able to pay our advertisers anyways. It doesn't matter. But Spark says, writing out to disk is kind of slow. Instead, what I'll do is I'll be the lazy teenager again. If I lose my homework, I'll just pretend I've done it. And then once you finally ask for it, I'll just do the part that I forgot. And that's it's not too bad an approach, right? Just recomputing the missing piece is often pretty cool. It can be a lot faster than writing your results out to disk on a bunch of different machines. And so this laziness gives us this implicit graph, and we can use this graph for resiliency. Part of it is we have to make all of our collections immutable, because if I did this recompute and I allowed you to mutate the previous state, my recompute would not necessarily make a lot of sense. But that's OK. Immutability, everyone loves immutability. Definitely no one wants to mutate collections. It's fine. It's fine. Everything's OK. I should have the dog there. OK, so there is a problem, though, because even though we are able to do this really cool pipelining, we're only able to do pipelining up until this action stage. And part of this is, unlike Heather's talk yesterday, which I don't know if y'all went to, Spark is notably not a compiler. It doesn't know everything that's going to be happening. It's just a library. It only sees up until this action. And so Spark, being lazy, will be able to optimize up until that point, but it doesn't know if you're going to need any of this data a second time around. It can't see into the future. We don't have the Marty McFly Back to the Future time machine. OK, 2 people saw that movie. But it's OK, right? We can just tell Spark manually when we want to reuse our data. And so this is a little bit hacky, right? Our magic is starting to The man behind the machine is starting to become visible, but it's not the end of the world, right? We can just paper that bit over and just tell Spark, I want to use this data again, and we can pretend everything's okay, and Spark works, right? Okay, some people with me. So the other magical part is the partitioning of our data, right? We loaded this data in, and I implicitly just assumed that it was going to be distributed on a bunch of machines. And most of the time, that actually works in Spark. If you're loading from something like HDFS, Spark will do a really good job of just like reading the data in, and the partitioning will end up being pretty similar to what the partitioning in HDFS was. The only downside if you start reading in what's called non-splittable data, or gzipped files, because no one likes compression, is then Spark just, it's not able to automatically split it for you for technical reasons that aren't super important. So sometimes we have to help Spark out by explicitly partitioning our data, which destroys a bit of the magic, right? I can't just pretend I have this magical distributed collection. I have to tell Spark how many pieces I want in my magical collection. But that's not too bad, right? It's just like specifying the parallelism. That's okay, right? I think things are going to deteriorate some more, so you better be okay with that part. So the problem is once we get to this, like, okay, Spark, I want you to split up my data some more for me. Spark goes, yeah, sure, I'll split it up. I'm going to make this object called a partitioner, and the partitioner will tell me where to send the different pieces of data. And Spark decided to use deterministic partitioning, right? Normally when we hear determinism in computer science, we're like, yes, I want my software to be deterministic. Non-deterministic partitioning sounds scary. Let's not do that. The only problem is my partitioner has to decide based entirely on my key data. And it turns out that you can have this thing called key skew. And the really inconvenient part about it is that key skew happens in the real world and not in my randomly generated sample data. Because I like picking uniform distributions. This looks very nice. But so the problem is, once we ask Spark to start partitioning our data, things can start to go downhill. And this can start to impact some of the operations that we're going to be doing on our data. So group by key, how many people have like a visceral reaction when I say group by key in Spark at the same time? Okay, there's like 5 hands, so most of you haven't used that. That's good. Never call group by key. And how many people have the visceral reaction when I say sort by key in Spark? 3 hands. I'm really sorry. Okay, let's talk about why those are terrible. So key skew comes to the anti-rescue, or as I like to call it, job security. So essentially, it turns out most of our data, like real data, has key skew. Humans, we cluster together in cities. Computers really like clustering together in this city called Null. It's their favorite city. They all really like to live there. Group by key explodes. It's not hard to make group by key explode in Spark. Honestly, like this is, as far as design decisions we made that were wrong, the group by key thing is just like one of those ones where I'm like, oh, I really wish I had a time machine because it would have been like a 1-character fix. But that's a story for 2 slides later. And the other one is like we can just have really unbalanced partitioners and partitions. And in that case, even more normal operations like sorting by key can fail. That normally happens with null. Null is the one which normally makes that part hurt. So here's an example of group by key in Spark. So this is, I've decided that I really want to get out of tech at some point in my life. I'm not sure if everyone else here has those feelings, but you know, I love computers, but one of these days, I would like to not wake up periodically and really just hope nothing's on fire. I want to wake up and feel optimistic about life, not wondering who hates me today. So I've decided the best way to do that is to open an artisanal mustache wax shop in San Francisco. Although actually, because I'm thinking about getting out of tech, I'm not sure if San Francisco is the place I should open my artisanal mustache wax shop. So I can buy some information about where mustaches are, right? Marketers have a lot of data. It's kind of scary. But I can buy that data from them for about $5. Alternatively, if they won't sell it to me, I can buy information about third wave coffee shops, which is strongly enough correlated with mustaches that we can make this work, right? So let's say I've got a bunch of records. So this is a zip code, and then probably your social security number, because I paid an extra 20 cents. And then, you know, maybe your mother's maiden name, in case I wanted to open a credit card. And then, so I group this together by key. And the problem is, it turns out there are just so many hipsters in the Mission District in San Francisco. So 94110 is the district I live in, and there's just too many handlebar mustaches. My computer fails, and I can't send you these exciting promotional offers about handlebar mustache wax. And this is very sad. I know you all feel sad when you don't receive special promotional offers. And so don't worry, the best minds of our generation are working on this problem. Only slightly depressing. So what do we do instead? So group by key is especially bad. So we can see here essentially what's happened is we have this zip code, and then we have this is a list. I like Python syntax too much. This is a list of tuples. And so essentially we have created a single record of all of the handlebar mustaches in San Francisco. Predictably, this message is too big to fit inside of the 2 gig partition limit. That's just going to happen. So it's OK, though, because I'm actually really only interested in figuring out where to open my mustache wax shop at this point. I could actually just go back to that word count example, and instead of doing group by key, I should actually probably use reduce by key. And then what happens is Spark will go, and on each of the partitions, it'll compute the number of people in each zip code, and then it'll shuffle the number of people in each zip code, and it can further aggregate it. And then my data works, and I can figure out, yes, the 2 most popular places for handlebar mustaches are San Francisco and Null. And as soon as I can find a lease in Null, I'll open my shop there. Aggregate by key, pretty similar. This is fine. We also get free map size reduction. That's pretty much fine. But it's OK. We can make this same problem explode just by sorting our data. We don't even have to do group by key. And this is the part which actually makes me feel really bad about our decision to enforce deterministic partitioning. Because group by key, at least I can probably tell you, here's an alternative. Please do this instead. But the alternative to sort by key is sufficiently bad that I feel bad. And it takes a lot. I've worked in software for a long time. So I'm willing to say close won't fix to a lot of things. So once again, handlebar mustache wax data, very important. But in this case, I've decided I want to sort this data. Maybe I'm going to sort it by zip code so I can figure out which people I should send these mails to. The problem is, now instead of not fitting in a single record, it just doesn't fit on the machine, right? In this case, the 10 records probably would fit on a machine, but if I was sorting my data for humans, quite likely San Francisco wouldn't fit on a single machine very easily. If I was doing this for my order data, it would be trivial, assuming my handlebar mustache wax shop doesn't do super well. But this is pretty bad, right? This sorting by key that should be a safe operation, right? If I can't at least sort by key, I've made a really not very good distributed system for you. But it's OK. What I can do is I can tell you, you just add some crap to the end of your key, and everything will be fine. And so it's like fine in the same sort of sense that a rusty spoon is fine. I can get a tetanus shot later, but it's expensive. And this is the problem. So what happens is, yeah, we can do this, right? I can manually add some crap to my key to allow Spark to be able to split, right? So this deterministic partitioner is able to introduce a split. The problem is, I had to add some crap to the end of my key. Now if I want to join this with another thing, I have to go back in and throw that crap out. Now that's OK, because the deterministic partitioner only applies during partitioning. So if I have a map stage, I'm not repartitioning my data in a map stage. I'm only doing it in a shuffle stage. So if I'm not currently partitioning, I can throw the crap out. It's fine. But on the other hand, we really should have seen this was going to happen, given just that it happens all the time. And there actually is a solution to this. One of the solutions is someone's been working on a non-deterministic partitioner support for Spark. The reason why we chose deterministic partitioning at the start, though, is really reasonable, right? If I know where my keys are, and I want to join with another thing where I know where my keys are, I can just do node-to-node communication. I don't have to do like another shuffle. And if I know where my keys are, and they're on the same machine, I might not even have to do any network communication to join two data sets together, right? That's what we want. We want co-located data where I don't have to do network communication. And I can only really guarantee that with a deterministic partitioner, which is why we chose it. It just turns out that like humans and computers and pretty much anything I have data about has enough key skew that I can't really take advantage of this very often. So that was a great decision. And it'll be fixed in the future. OK, here's an example with literally kilobytes of data. We've got a shuffled read of 48 kilobytes, and I'm running low on time, so we're just going to move ahead. You can see here I have a shuffled read of a fourth of that. Smaller numbers are good. In this case, it's not revenue. So we can see that when we replace our group by key for reduce by key, we're happier. The dog is even happier. All around, good win. So this is, I already told you all of these things, but if you forget, there's a slide. Yay. OK. Arbitrary functions. So this is a really important principle of Spark. It means that you aren't just limited to like SQL or something, right? Not that there's anything wrong with SQL. It's a great language, but you can write your arbitrary Python functions. You can write your arbitrary Scala functions. If you're really out there, you can write your arbitrary C# and JavaScript functions and run them on your big data. If you're doing them on JavaScript, I know someone that really wants to talk to you, but if you're not, that's probably more normal. So the problem is that our optimizer with arbitrary functions doesn't know what we're asking it to do, right? Some of you may have been like feeling a little bit cheated when I was saying don't use group by key, because you can be like, Holden, like if you group it by key and then you apply a reduction to your grouped set, like if I do a group by key and then I compute the sum, right? Why doesn't Spark just pipeline that sum for me? And the reason is the sum is implemented in Scala or Python code, and Spark has no idea that you want to compute the sum. It just knows you want to compute something over this list, and it's going to do that for you, but it doesn't know how to help you. And this is part of the motivation for Spark DataFrames. And we're gonna move quickly now so we can get to that. Yes, OK, sadness. We can combine key skew with black boxes to make Spark even sadder. This is bad word count. The second part of the word count example that doesn't normally make it into the big data talks. We use group by key and map values, and Spark has no idea that we're asking it to compute the sum, so this just performs really poorly. But it's OK. We have someone who's offered to save us. Yay! OK. Available starting in Spark 1.3, which has been available for a really long time now. So please, DataFrames are really awesome. You can use arbitrary lambda expressions with DataFrames, but the nice thing about DataFrames is you don't always have to use arbitrary lambdas. If you're going to group by key and then compute the sum, or you are going to compute a bunch of different aggregates, you can actually do this in a much more expressive syntax that Spark is able to understand, and the optimizer is able to help us. It's not like complete magic, but let's look at some of the magic. So here, the other part that this is able to do for me is push down filters to my data store level. And this is really awesome because I'm super lazy, and whenever I'm writing code, I don't normally think about like, I've got this filter, I should probably take that up and apply that to where I was reading my data in. So here, I'm reading in information about pandas, and I only want to know about the happy ones because the sad ones make me sad. So I want to compute the fuzziness. And so I've got this filter expression and this thing to compute the fuzziness. Now, the thing to compute the fuzziness is a Scala expression. The thing to restrict it to happy pandas is a special Spark SQL expression. You can tell because we put an extra equal sign in there. It makes it magical. But what happens is Spark is actually able to understand this expression. I mean, the syntax, very reminiscent of Perl. We love that $sign. But we're able to push this down to the data store for you for free. And so that's pretty awesome. Yeah, cool. I specify the types here because I like types. And type inference, it turns out it's hard. And so we didn't bother doing it in a lot of places. But there's probably only medium amounts of excitement. I can definitely tell the laughter's gone down. So we're going to go on to the really exciting one. Yay! The talk is almost finished, I promise. So the other thing is we can actually, we still have our arbitrary lambda expressions, right? If writing in Spark's weird little SQL-like DSL doesn't feel very natural to you, you only have to use it in the places where it's really important. And the rest of the time, you can just write your fun lambda expressions. You can have all that fun being a functional programmer and just, you know, party. I used to put this example on and say, you can do things that are like difficult to do in SQL, and someone just pointed out to me that I'm just really bad at SQL. So, yeah. Okay, right, yay, here's a graph. You should trust this as much as you trust graphs from vendors. Bigger numbers are bad. Smaller numbers are good. Smallest number is thing I'm telling you is good. Please buy 6. Yeah, TLDR. Right, whenever anyone tells you things work really well, you should ask them how they're going to explode. And these is a non-exhaustive set of ways that DataFrames are worse than RDDs. If you're doing machine learning on them, even though Spark's machine learning exposes a data frame API, iterative algorithms perform really terribly. We actually just hide everything from you and do it on RDDs. Long story. Ask me when I'm drunk. The pushdown thing that I told you was amazing, only works some of the time. Probably not the most surprising thing in the world. It depends on your different data sources and what they support. The wonderful thing about this is that we added a whole new set of knobs for you to tune in your Spark jobs. And they're just really well documented. And very easy for you to figure out what they should be set to. And yeah, the other thing is like a lot of these default numbers we picked are great for the word count example, kind of terrible for production data. So you get to go and ask people on the user mailing list, what did you set like foobar to? And they'll say 7, and then you set it to 8, and hope for the best. Let's see what time it is. Ooh, okay. Yeah. I'm gonna breeze through this part. We're gonna have Spark on non-JVM languages. It's already there. We support Python. Some people made it work with C#. Coincidentally, they work for Microsoft. Largest surprise ever. Our support, actually, that person, several people work on it. One of them is at Microsoft. Really nice guy. And essentially, this part of the story is perhaps not super exciting to people, but it's essentially a study in how expensive inter-process communication can be. And it turns out pretty expensive is the short version of all of the slides I'm going to skip now. Okay, and instead, we're going to focus on the future. The future is this thing called Apache Arrow. Has anyone heard about Apache Arrow? Yay! Is Wes in the room? Yay! Okay, so if you have any questions about Apache Arrow, go talk to Wes. But more seriously, we're hoping to start using Apache Arrow more frequently for interchange between these different languages, also for when we're working with GPUs and other fun things. It is possibly the future. I really hope so. The alternatives are strings, and strings make me sad. And yeah. Is that your logo, by the way? I just found something on Twitter. Okay, cool. So this is the Apache Arrow logo over a cat who is having a really good time. Yeah. Okay, so for most of these things, normally I would end with patches welcome, but that would be a lie. Patches really aren't welcome for any of these things. It's unfortunate, but essentially, even though Spark is open source, these are really core design decisions, and we need to work around a lot of these things. But if you just show up with code randomly on the mailing list, people will be like, oh, no, I don't want to do that. So it's going to take a lot longer. There's this process called SPIP for suggesting large changes to Spark. If you have ideas about how to do this, consider writing one of those. At the same time, you might want someone to pay you. So consider writing a thesis proposal, but they won't pay you a lot. But UC Berkeley. The alternative option is you can just go and build other systems that don't recreate our mistakes. I would prefer it if you fix Spark. I make money in Spark. vaguely somehow. So yeah. OK, that's a depressing end. If anyone doesn't know Spark and I haven't scared you away from it, Paco has a wonderful introduction video. More importantly, though, oh, no, let's skip testing. That's not a big deal at all. You should buy several copies of my latest book, High Performance Spark. That quarter of a cup of coffee won't pay for itself. And honestly, if you want to learn Spark, learning Spark or learning PySpark, probably better options. I don't get a lot of money. I didn't even write this one, and I still think it's good. Really great people. OK, yeah. Cats love it. No returns, please. Ooh, if you want excuses to come go to fun cities, here's a bunch of places I'm going to go give talks at. And really, that's pretty much it. Thank you all for staying.